Okay, hello everyone, in a new video. So we have reached part 4 of chapter 3, which is the chapter of electric current for grade 10 students. So now in this one we are going to finish this chapter and solve some exercises. Then exercise number 6, they are telling me figure 1, so they mentioned figure 1, now we can use it. It's a circuit diagram that shows the combination of 6 electric dipoles. And here let's recall what's the meaning of a dipole. Pole means a terminal and di means 2, so this is a dipole. So almost in all of the cases the electric components that are considered in an electric circuits are dipole, but also there are other electric components that are tripole, like the rheostat, or say for example the transistor, that are connected to a battery of 24 volts. So the trick in solving such type of exercises is to write the voltage on the electric circuit itself. An analog voltmeter with non-centered needle used with a scale of 10 volts is connected across the terminals of C and N of D6. The screen of this voltmeter is represented in figure 2. So they mentioned figure 2, now we can also use it. So also it's better to write the scale under the figure. Now this measures either UCN or ENC, and this depends on the COM terminal. Now what does each of these numbers indicate? 100 represents the total number of divisions, then D is equal to 100 divisions, which is the dial, and the pointing of the needle represents the small d, which is equal to 80 divisions. Okay. Now part A, they are telling me given that UAC is equal to 6 volts, so here we have that UAC is equal to 6 volts, and UCB is equal to minus 4 volts. Now number 1, they are telling me verify that the potential difference across D6 is UCN is equal to 8 volts. So notice that here in this case we are interested in determining the voltage UCN, but we cannot use the law of addition of voltages because we have another unknown at least, which is UPA. So this system is undetermined. However, by referring to the reading of the analog voltmeter, we can determine the value of UCN. Moreover, they are telling me it's measuring UCN, and it's given by UCN is equal to S multiplied by D divided by capital D, which is given by 10 multiplied by 80 divided by 100, which is equal to 8 volts. So in this case, UCN is equal to 8 volts, and the trick in solving such type of exercises is to write the applied voltage on the electric circuit itself. Then UCN is equal to 8 volts. Now in number 2, calculate UBC, so this is comma, UBC, UPA and UAB. Then the voltage UBC can be determined, okay, it can be determined directly because we know UCB. So UBC is equal to minus UCB, which is equal to minus multiplied by minus, which is equal to 4 volts. Then in this case, UBC is equal to 4 volts. Now as for the voltage UPA, so this can be determined by using the law of addition of voltages. So notice that if you consider this loop, then the only unknown is given by UPA, then apply law of addition of voltages. Then on the left hand side of this equation we write the voltage we are interested in determining, which is given by UPA, and on the right hand side we'll go from P to A across different electric components such that you know the voltages from P to N, from N to C, and from C to A. So this is equal to 24. Okay, if this is 8, then UNC is minus 8, and this is UCA plus minus 6. This is equal to 10 volts. So UPA is equal to 10 volts. Everything is expressed in the SI, and this is a linear equation in 1 unknown. So now before looking at the question, the only unknown is the voltage UAB, so we are expected to be asked about the voltage UAB. Then on the left hand side of this equation we'll write the voltage UAB. So we will consider this slope, which is the triangular, then from A to C and from C to B, which is equal to 6 plus minus 4, which is equal to 2 volts. Then UAB is equal to 2 volts. So this is it for part 2. Now in number 3, eventually they are telling me that C is taken as a reference electric potential, and we are interested in determining VC, VA, and VN. So let's start by VC, which is VC is equal to 0, and the reason is given by reference electric potential. Now we are interested in determining the electric potential at the point A. So in order to determine the electric potential at A, we need to consider another point in which we know the electric potential at that point, and the voltage that relates the 2 points, which is given by UAC. So UAC is given by 6 volts, and in this case VA, which is the unknown, is encoded in this equation because VA minus V6 is equal to 6. We are interested in determining VA. So VA minus 0 is equal to 6, which means that VA is equal to 6 volts. So we are done with part VA. Now as for VN, so let me say electric potential at N. So in this case we are interested in determining the electric potential at the point N. Then we need to consider another point in which we know the electric potential at that point and the voltage that relates the 2 points, which is given by UCN, is equal to 3 volts. So now Vn is encoded in this equation because Vc minus Vn is equal to 3, and we are interested in determining this. So what's the type of this equation? It is a linear equation in one unknown. The unknown is Vn. Then in this case Vn is given by Vc minus 3, or let me say the following, that in this case Vc is 0, so minus Vn is equal to 3, and Vn is equal to 3 volts. And we are done with part A of this exercise. Now in part B they are telling me a determination of the intensity of the electric current. So this exercise consists of 2 parts, part A and part B. Part A is discussing the law of addition of voltages, and in part B we are discussing the law of addition of currents. Determination of the intensity of the electric current. Okay, the intensity of the main current I is equal to 2.5 amperes. So starting from the battery, this is a main current, a main branch. This is a sub branch. All of these are sub branches, and this is a main branch. So the current traversing the main branch is given by I is equal to 2.5 amperes. So let me label them in blue. And the current traversing D2 is I2 is equal to 0.5 amperes. Now, okay, the current may traverse across D2 from A to B or B to A. So notice that because the main current is traversing from the positive pole to the negative pole, so this is straightforward that it will be from A to B. Moreover, looking at the potential UAB, it's positive, which means that from higher potential to lower potential, which means from A to B. So from A to B, and the electric current in this case is given by I2 is equal to 0.5 amperes. Okay. Now number 1, they are telling me show on the figure the direction of the electric current in the circuit. So we need to show the electric current in each branch. and by show it means that we need to justify. Always it's better to justify. Now let's take the branch PA. So notice that the voltage UPA, or let me say at the beginning, that since the electric current traverses from high potential to low potential. So in the branch PA, so we have that UPA is equal to 10 volts, which is positive, which means that VP minus VA is positive, which means that VP is greater than VPA. Then it's from P to A, okay, in the branch PA. Now as for the branch AB, notice that UAB is equal to 2 volts, which is positive. VA minus VB is equal to 2 volt is positive, which means that VA is greater than VB, and in this case from A to B. So also this is a branch of AB, so it will be directed like this from A to B. Now we are left with the branches AC and BC. So let me say here branch AC. So we have that 2AC is equal to 6 volts, which is positive. So VA minus VC, which is positive. So VA greater than VC, which means from A to C. Okay. Now as for the branch BC, so notice that here UCB is negative, which means that VC minus VB is negative, which means that VC is less than VB. So in this case, it always traverses from B to C, from higher potential to lower potential, then in this case from B to C. Okay. So now as for the potential, as for the branch C, and we can also justify. So in this case UCN is equal to 3 volts, which is positive, which means VC minus VN is positive, which means that VC is greater than VN. So in this case it's simply from C to N. Okay. Now number 2, they are telling me calculate I5, the current traversing D5. Calculate I5, the current traversing D5, knowing that 9.375 times 10 to the power 18 electrons flow in the branch AC during 2 seconds. Okay, so we are interested in determining the current I5, which is this current here. But since they specify the number of electrons and time, we must think of the formula, which is given by I is equal to Q over T, which is the rate of charge. Okay, now knowing that Q can be determined by N times E, in which N is the number of electrons, which is given by 9.375 times 10 to the power 18, and E is the elementary charge, which is given by 1.6 times 10 to the power minus 19, which is the charge of an electron. Plugging this on the calculator, then the value of Q is given by 1.5. Since everything is expressed in SI, so the value of Q is in SI, which is coulombs. then Q is equal to 1.5 coulombs. Now after we have determined Q, we can determine the value of I, because I is given by, so I5 is equal to the charge located in the, or moving in the charge in the branch 5 for t, and t is given by 2 seconds. So 1.5 divided by 2, this is equal to 0.75 amperes. Then the value of I5 is equal to 0.75 amperes. And now after we have determined the value of I5, let's label it on the electric circuit. So here this is 0.75 amperes, which is I5. Okay, so the value of I5 here is given by 0.75 amperes. Now in part 3 they are telling me determine I3 and I4, the intensities of the currents flowing through D3 and D4 respectively. So notice that in this case we know the current in D1, which is 2.5, we know the current here, which is 0.5, we know the current here, which is 0.5 amperes. Then applying the law of addition of currents at the node A, we can determine the current traversing D3. Then apply law of addition of currents at node 3, at node A, sorry. Now the law of addition of currents is given by summation of I in is equal to summation of I out. Let's determine the currents that are entering the node, and this is only given by the main current, which is I. The currents leaving the node are given by I3, I2, and I5, and this is the correct direction of the current because we have predetermined this according to the value of the potential difference, which is U. Now so here we have I3 plus I2 plus I5, and we are interested in determining the value of I3. Then I3 is given by I minus I2 minus I5, which is equal to, the value of I is 2.5, the value of I2 is 0.5, and the value of I5 is given by 0.75. Plugging this on the calculator, then the value of I3 is given by 1.25. Everything is expressed in SI, which is amperes. So in this case, I3 is equal to 1.25 amperes. And now let's determine the current D4 traversing this branch. Notice that we can apply the law of addition of currents either at point B or at point C. Let's take for example the point C. So it's the same. So apply law of addition of currents. So here addition of currents at node C. We have that summation of I in is equal to summation of I out. So what are the currents that are entering the node given by I4 and I5? And the current that are leaving the node is given by I6, and we are interested eventually in determining the value of I4. So I4 is equal to I6 minus I5, which is equal to, so the value of I, which is I6, is given by, so this is I, by 2.5 minus I5, which is given by 0.75. So this is equal to, we have 1.75 amperes, right? So because 25 for it to be 1 and 1.5. So the value of I4 is equal to 1.75. And you can double check here that this current added with this current will give us 1.75 amperes. Then this is it for this exercise. Let me move to the other exercise, which is exercise number 7, which is the last exercise. The figure below shows a circuit containing a generator of direct voltage UPN is equal to 12 volt. Let me correct this, and this is given by UPN. So the voltage here is given by UPN is equal to 12 volts. 6 resistors A, B, C, X, Y, and Z, and an oscilloscope. The switch key is closed, so this is the simplest case. Now yet we didn't study what's meant by resistor, but now we consider it as a general electric component, and we will not discuss the different laws that is governed by or across a resistor. Okay, so now number one, the switch key is closed. We connect the oscilloscope so that we visualize the voltage UAB. So this oscilloscope is measuring the voltage UAB. We notice that the luminous line is deviated by 3 divisions. Okay, show the connection of the oscilloscope on the figure. So let me say, since the oscilloscope measures UAB, then the phase terminal is connected to A, and the mass terminal is connected to B. So these are the connections of the oscilloscope. Since it's measuring UAB, then this is the phase terminal and this is the mass terminal. Okay, so we are done with part A. And part B, they are telling me in which direction does the luminous line deviate. Here there is something missing, and let me say that knowing that UVA is negative. Okay, so why UVA is negative? Sorry, knowing that UVA is positive. So how come me as a teacher I know that UVA is positive? Because simply this is the main branch connected to the battery, so the direction of the current will be like this, and here it will be like this, because this is a main branch from the positive pole back to the negative pole. So it's reasonable it will be something like this, because it will be like this because this circuit only consists of one generator. So because it's being traversed from B to A, then B is of higher potential and A is a lower potential, which means that UVA is positive. Now other than that, now I'm considering that I gave you the following given, which is knowing that UVA is positive. So let me say if this is part A and this is part B, and let me say since the measured value is positive, they are talking about the displacement of the luminous line. It will be displaced upward or downward depending if we are measuring positive or negative voltage. Now here notice that we are measuring negative voltage, which is UAB. Then the luminous line will be displaced downward. So here the measured value is given by UAB, which is negative because we know that UBA is positive. Now in part C, calculate UAB. So it's given by SV times Y, knowing that the vertical sensitivity SV is given by 3 volts per division. And here we know that is displaced 3 divisions. So Y is equal to plus 3 divisions because now it's, minus 3 divisions because we know it's downward. So it's equal to 3 multiplied by minus 3, which is equal to minus 9 volts. So UAB is equal to minus 9 volts. Now in number 2 they are telling me by using the additive law of voltages, find the voltage across the resistors C, X and Z. So let me first start with C. So apply law of addition of voltages. So on the left we are interested in the voltage across the resistor C. We can either determine UBR or URB. Let me say UBR, which is equal to UBP plus UPN plus UNL plus ULR. So UPP is 0 because we have a connecting wire. Now UPN is given by 12 and UNC, sorry, this is UNL. UNL is 0 connecting wire. And ULR also 0 because it's a connecting wire. So in this case, this is equal to 12 volts. So UBR is equal to 12 volts. So now as for the resistor X, so apply law of addition of voltages. So on the left hand side we are interested in determining the voltage across the resistor X, which is given by UAR or URA. Let me consider UAR because I know it's positive. If you consider URA, it's the same. So from A to B, which is UAB, plus from B to C. So UAB is given by minus 9 plus 12, which is equal to 3 volts. So UAR is equal to 3 volts. And let me write it down here. Now let me say apply law of addition of voltages in order to determine the voltage Z, which is given by USZ. Here you can directly say that USZ is equal to UBA because according to the law of uniqueness of voltages, they have the same voltage because they are in parallel. But it's more elegant to apply the law of addition of voltages. So on the left hand side we write the voltage that we are interested in calculating, which is the voltage across Z, which is either USJ or UJS. In this case I will consider USJ because it's positive, which is equal to USB plus UBA plus UAJ. So this is 0 plus minus, sorry, if UAB is minus 9, then UBA is plus 9. And this is 0. Let me justify between brackets that USB is equal to 0 and UAJ is equal to 0. The reason is given by connecting wires. So this is equal to 9 volts. Then USJ is equal to 9 volts. So we are done with part 2 also. Now in number 3 they are telling me what is the value of UMB and UNM So where is the point? Okay, so we need to determine U and B. So U and B, so let me say the voltage across a closed switch is 0 since it acts as a connecting wire. So U and B is equal to 0. And now we need to determine the voltage U and M, which is the voltage between the points N and M. So we can go from N to P, P to B, and B to M using the law of addition of voltages. Although across the points, so N and M, we can look and do different ways from A to H, H to L, and L to N, but we don't know these voltages, so we can go directly from N to B, B to P, from N to P, P to B, B to M, because we have discussed the voltage across the closed switch. So let me say apply law of addition of voltages. So we are interested in determining U and M. So from N to P plus P to B and B back to M. Now U and P is given by minus 12, because if your Pn is 12, then U and P is minus 12. This is 0 discussed previously, and this is 0 discussed here. So this is equal to minus 12 volts, then U and M is equal to minus 12 volts. And let me say here that U and M is equal to minus 12 volts. So we are done with part 3. Now in part 4 they are telling me show the direction of the electric current in all branches of the circuit. So we will solve this exercise based on the fact that electric current always traverses a branch from higher potential to lower potential. So let me start with the branch BR. So okay, this is a main branch, so the electric current will be like this, because from the positive pole back to the negative pole. Now the branch BR, UBR is equal to here 12 volts, which is positive. So VB minus VR is positive, then VB greater than VR, which is from B to R. Now as for the branch BA, so UAB is equal to minus 9 volts, which is negative, then VA minus VB, which is negative, then VA is less than VB. So in this case from B to A. So from B to A like this, and in this case also like this. So now what I will do, I will erase the value of the voltages that we are not using anymore. So let me get rid of this one and also get rid of this one. Now as for UAR, branch AR, we have UAR equal to 3 volts, which is positive, which means that VA minus VR is positive, which means that VA is greater than VR, which means from A to R. So now look at this. If all currents are entering this point and leaving here, so it's reasonable, then the electric current will be like this, okay? Although this, okay, so it's like this. Now what's left is the single branch, which is given by from N to M. So they are all in series, then they will have the same direction. So let me say branch NM or MN. So we have that 2NM is equal to minus 12 volts, which is negative, which means that Vn minus Vm is negative, which means that Vn is less than Vm. So in this case, simply from M to N. So in this case, the current will be traversing like this from M to N. Okay, and this is reasonable because this is the main branch and the current will split at this point in all directions, as if leaving the node. So we are done with part 4. And here let me erase these voltages. Now in part 5 we need to complete with the justification the table below. The table consists of 2 rows. The first row is the branch and the second row is the intensity of the current, which is the value of the electric current. So here let me label the currents in different branches. So in the branch Pn, the value of the current is given by 10 milliamps, which is 0.01 amperes. Recall that in order to convert from milliamps, or let me leave the value of the currents in amperes. So this is 10 milliamps. So knowing that milliamps is not a SI unit of current, in order to convert from milliamps to amps, we divide by 1000. Now in the branch BA, this is the branch BA, which is given by how much? 2 milliamps. And the branch BR is given by 3 milliamps. Now in L, okay, so and the branch BM is given by 4 milliamps. So this is 4 milliamps, 4 milliamps, and 4 milliamps. So the missing currents are given in the branches LH. So okay, in SJ and AR and RL. So let me start directly with the branch LH. So notice that BM, MH, and HL are in series. So let me say that MH, the components, this is B, the components, so this component is being traversed by the current 4 milliamps. Then also for the component A, let me say that B and A are in series. According to law of uniqueness of currents, they have the same current. Which is that the current of B is equal to the current of A, which is equal to 4 milliamps. So here we have also 4 milliamps. Okay, now as for SJ, so now let me say branch SJ. Now SJ represents this. Now we can apply the law of addition of currents at the point B. we have that summation of I in is equal to summation of I out. So what are the currents that are entering the node? We have this, which is given by 10 plus, so this is it, and the currents that are leaving, they are given by 4 plus 3 plus 2 plus the unknown current, which is IZ. Then I across the components is given by 10 minus 4 minus 3 minus 2, and as expected this must be positive because our directions are correct. So it's given by 1 milliamps. So IC is equal to 1 milliamps. Here no need to convert to the SI because simply the table is being labeled by milliamps. So this is 1. Now as for AR, then we are interested, so this is 1 milliamps. We are interested in determining the law of addition of currents at node A. So for a branch AR, so apply law of addition of currents at A, let me say better at node A, so summation of I in is equal to summation of I out. So the currents that are entering are given by 2 plus 1, which is equal to the current that you are interested in calculating, which is Ix. These are the currents entering 2 and 1. So Ix is simply given by 3 milliamps because the entering currents are expressed in milliamps. So this is 3. Now finally, as for RL, so let me say branch RL. So apply law of addition of currents at node. We can either apply it at node L or R, but say for example R. Then summation of I in is equal to summation of I out. So the currents entering at node R, so this is given by 3. So 3 plus 3, and the current leaving are the current I, which is say for example RL. No, we cannot use this notation. Say I prime, whatever. So I prime is equal to 6 milliamps. Okay. So, and here there is something wrong. How come 6 and 6? Okay, no, correct. Now if this is 6, 6 plus 4, it will give me 10, which is the main current. Okay, so this is 6. And by this we have finished solving this exercise. So that's it for me in this video, guys, and in the coming video we'll start chapter number 4, which is the resistors.